All right, so this is section 6.8, L'Hopital's rule, video number 2. So we've learned how to do L'Hopital's rule if we have a form of some kind of a limit on the numerator of 0 divided by a limit of the denominator being 0, or some form of infinity over another infinity. But we might not exactly have that form right up front. You might get something that looks like this: 0 times infinity. It'd be really nice if we could just say that 0 times infinity is 0, because we've learned that 0 times anything is 0, except that it has to be a number. Infinity is not a number, it's a concept. So we can't just say that 0 times infinity is 0. We also can't say that infinity times anything is infinite, because, again, we're multiplying it by 0. So infinity times a regular number would be infinite. That would be correct. But not multiplied by 0. So that's a possible form. We could also have 0 times negative infinity, which, again, because that's a concept, we can't just say that it's 0. And then we could also have some form of infinity minus some other form of infinity. These are all forms that we can possibly still find the limit of. We just have to do a little bit of algebraic manipulation. Now, if you have infinity plus infinity, well, if you take a really super large number and you add it to another super large number, you're just going to get an even bigger super large number. So you would get infinity if you're adding two infinities together. The problem is infinities can grow at different rates. So one infinity minus another infinity might not be 0, might not be infinity. It might actually just be a regular number, and you have to do some work to find it. All right, so let's take a look at a few examples of where you might see these. And if you get a form that looks like this, you just have to try some algebraic manipulation first. So the first thing is, the limit as x approaches 0 from the positive side of x ln of x. So if you were to plug 0 into x, that's obviously 0. If you're to plug 0 into the natural log of x, it doesn't exist. But as x approaches 0, now again, you have to remember what the graphs look like. Natural log of x looks like this. So as you approach 0 from the right side, this thing is going towards negative infinity. So what you would get here is some form of 0 times negative infinity. And again, that's an indeterminate value. Okay, but we can manipulate this algebraically so that it'll give us a form that we can use. It has to be in the form of some kind of 0 over 0 or infinity over infinity. So the first thing we're going to do is we're going to try to rewrite this algebraically. Okay, well, the natural log of x, as x approaches 0 from the right, is already in the form of negative infinity. So I'm going to leave that one alone. But I can rewrite multiplying by x as dividing by 1 over x. And if you're like, well, wait a minute, how would you figure that one out? Just remember, if you divide by a fraction, it's multiplying by its reciprocal. So if I'm going to divide by 1 over x, it's the same thing as bringing that up, flipping it over and multiplying by x. They are the same thing. But now I have to ask myself, well, what does the graph of 1 over x look like? Well, 1 over x looks like this. So as x approaches 0 from the right side, 1 over x approaches infinity. It's going to keep going up. So now what I have is negative infinity over positive infinity. Best to put that little arrow there so we know it's not really equal to that. It's just what it gives us there. But now it's in the correct form to use L'Hopital's rule. So I can now take the derivative of the numerator and the denominator separately, and then we'll try and reapply the limit. The derivative of natural log of x is 1 over x. And remember that the denominator is technically x to the negative 1, so that's negative x to the negative 2. So now rewriting that limit, so I'm going to get 1 over x in the top, and that denominator is really going to be negative 1 over x squared. Now, if you were to plug 0 into both of the numerator and denominator, once again, you would get infinity over infinity, or some form thereof. And the problem with that is we haven't actually simplified anything. Let's algebraically simplify this before we try to reapply the limit. Remember, dividing by a fraction, again, is multiplying by its reciprocal. So really what I have is the limit of 1 over x times negative x squared over 1. And that's going to end up being negative x squared over x, which simplifies just to x. So really what I have here is the limit as x approaches 0 from the right of x. That I can directly substitute in, and we get 0. So you do have to do a little bit of algebra, but it can still be done. All right, let's move on to number 2. Now in number 2, you really have to know your trig stuff here. The limit as x approaches pi halves from the left-hand side of secant of x minus tangent of x. You have to go back to your graphs of secant and tangent, or at least understand how they work. I'm not going to walk through the entire process there, but secant of x as x approaches pi halves from the left goes to infinity. Tangent of x as x approaches pi halves from the left also goes to infinity. So we get infinity minus infinity. Again, we can't just say that that's going to be 0. We can't say that it's going to be infinity. We can't say that it's going to be a number. We have to do some work to show it. Obviously, you could guess, but then you probably wouldn't get any credit for it. So let's go ahead and try and rewrite this. Use some trig properties here and rewrite this. So I can rewrite secant as 1 over cosine. And I can write tangent as sine over cosine. So to me, that made sense simply because of the fact that they are both the same denominator. If they weren't the same denominator, we might want to try something different first. Pi halves from the left. So let's go ahead and write that as 1 minus sine of x over cosine of x. So now if you directly substitute pi halves into your numerator, we get 1 minus the sine of pi halves. Sine of pi halves is 1, so you get 0 in the numerator. That's still okay, as long as we don't have 0 in the denominator. But alas, cosine of pi halves is also 0. So we would get 0 in the numerator and denominator. So now we can apply L'Hopital's rule because we did have the right form. So if we apply L'Hopital's rule, we'll now take the limit as x approaches pi halves from the left, take the derivative of the numerator. The derivative of 1 minus sine of x is going to be minus cosine of x. The derivative of cosine of x is negative sine of x. The minuses are going to cancel out, but that's ultimately not going to matter because if I directly substitute pi halves into the numerator, cosine of pi halves is 0. Sine of pi halves is 1. I would get 0 over some actual number here, so my limit is 0. So we actually did. In this case, the infinities must have been growing at the same rates because infinity minus infinity gave us 0. Okay, number 3 is a bit more tricky. It's not terribly difficult, but you probably wouldn't normally think to do this. This is why I put this one on here. If you were to plug in infinity, x goes to infinity, the natural log of x also goes to infinity. So once again, you would have an infinity minus infinity. This one's not as easy just to rewrite because there's no common denominator. I can't make these things into like something over cosine or, whatever that we did from the previous problem. Can't do it that way. What you can do, however, and this is a strange thing to think about, is I can factor an x out. And no, that does not mean I can take the x away from the natural log. The argument of that stays the same. Basically, I am dividing each term by x when I factor it out. So what you will get is the limit as x approaches infinity of x on the outside of the parentheses. Now, if I divide an x out of each term, x divided by x is 1. The natural log of x divided by x is literally just the natural log of x divided by x. Not much else we can do with that. So now you have to use a little bit of what we've done in the past. If I were to directly substitute infinity in for x, on the outside I would get infinity. On the inside, you have to look at this piece right here because the one part's going to stay the same. This piece right here is the one we have to figure out. 1 is still 1. If I were to directly substitute infinity, yes, I would get infinity over infinity. But now's where you have to ask yourself about these growth rates. Because we're approaching infinity, does the natural log of x or x grow faster? And the answer to that question is x. Polynomials will grow faster than logs all the time. So in this case, the denominator grows faster than the numerator, which means that that piece, the natural log of x over x, goes to 0. So ultimately what I get is infinity times 1, and infinity times an actual number is infinity. So really that means that that limit doesn't exist in the positive direction. It's just going to keep on getting bigger and bigger off towards infinity. All right, and then our last problem, number 4, once again, if I were to plug in infinity for all the x's, you would get the square root of some kind of infinity squared, which is some other form of infinity minus another infinity. So once again, we would get an infinity minus infinity. Okay, this one's a little bit trickier. You definitely have to do a bit more work here. In this case, I can create a fraction by putting anything over top of 1. So I'm going to put that whole thing over 1. The only reason I'm doing that is because I can think to myself, well, wait a minute, if I do that, this kind of looks like one of those conjugate type problems. And that's exactly what you're going to have to do here in order to manipulate this one a little bit. Because remember, the ultimate goal is to get it to some form of infinity over infinity or 0 over 0. I can take the original function that I just wrote and multiply it by the conjugate on the top and the bottom. So x squared minus 7x plus x on the numerator and the denominator. And again, this is probably not something you would think to do, so that's why I'm showing you the example. Well, let's go ahead and simplify everything. So now if I use the conjugate method on the top, I'm just going to get the x squared minus 7x, and then minus x squared from multiplying the last times the last. I'm just going to go ahead and keep the denominator the way it is. Okay, still got a little more simplification to go because the x squareds in the numerator are going to cancel themselves out, which is nice. So now I get negative 7x on top over the square root of x squared minus 7x plus x. And now what we get is some form of infinity over another form of infinity. And if you're really careful about this, while I could apply L'Hopital's rule to this, because I do get infinity over infinity of some form, I can look at the growth rates on the numerator and the denominator on this one and be able to figure this out. The growth rate on the numerator is linear. So I'm going to get that that's a linear function. Technically, the growth rate in the denominator is also linear because you only look at the highest power terms. Well, the square root of x squared is x. So that's really going to be the dominant term, but I also have an x from this one right here. So if I add the leading coefficients of the denominator together, that's going to be a 1 from this one and a 1 from this one. I get 2 in the denominator, and I get negative 7 in the numerator. Okay, that's a shortcut. Or you could have applied L'Hopital's rule. Take the derivative of the numerator, you get negative 7. If you take the derivative of the denominator and then reapply the x approaching infinity, you would get negative 7 halves. All right, that one is a much shorter video, and hopefully that will be enough.